All right, so finishing up our notes on logistic functions, we're going to take a look at this next example here. It says the population P of T of fish in a lake satisfies the logistic differential equation dP dt is equal to 3p minus p squared over 6,000. And T is measured in years, and P of 0 is equal to 4,000. So that means your initial population of fish in the lake is going to be 4,000. All right, so what we're going to do is take a look at several different parts of this problem here. So this one is worded a little bit differently on this particular problem. We are given the differential equation, and one of the things we want to think about is what is our formula for our differential equation. So if we go back to the original formula, that was dP dt is equal to Kp times 1 minus P over M. So what we want to do is try to get this equation into this format right here, because if we can do that, then we can determine what M is, which is your carrying capacity. And so with that, we can do this by factoring a 3p out of this problem. So if you factor 3p out of this problem, what that's going to leave you with then is 1 minus p over 18,000. And you can think about this in terms of if you multiply 3p times 1, you get your 3p right here. And if you multiply 3p times this, p times p is your p squared. 3 over 18,000 reduces to your 6,000 in your denominator. But we like this format right here because this tells us that M, which is our carrying capacity, is 18,000. Well, if your carrying capacity is 18,000, that means the limit as t approaches 0 is going to be 18,000. Okay. All right, so question here then, part B, is what is the range of the solution curve? All right, well, the solution curve, we want to start out right here with our initial population, which P of 0 was at 4,000. So the range are your y values, which go from 4,000 up to 18,000. 4,000 is included, so it's a bracket. 18,000 is an asymptote, so that is going to be your parentheses. All right, so it's not included. So part C, for what values of P is the solution curve increasing, decreasing, and justify our answer? Well, we know that P is always increasing on this type of problem because our growth curve is continually increasing. Now, how do we know this? Because what you want to look at is when dP dt is greater than 0 and our derivative dP dt, which is this right up here, is greater than 0 on the entire domain of 4,000 to 18,000. All right, so then part D says find the second derivative and use it to find the values of P for which the solution curve is concave up and concave down, and then we need to justify our answer. All right, so on part D, let's do that down here. the second derivative is equal to 3 minus p over 3,000. And if we set that equal to 0 and solve, you're going to end up with p over 3,000 equals 3, so p is equal to 9,000. And if we do a sign chart with this, where we have an initial population of 4,000, 9,000, right here for our second derivative equaling 0, and do a sign chart with your second derivative. This is positive and negative, and so therefore if we look at concave up, our function is going to be concave up between 4,000 and 9,000 because the second derivative is greater than 0. And our graph is, or our function is going to be concave down between 9,000 and 18,000, which is our ending amount here, or carrying capacity, because the second derivative is less than 0. Those are your justifications. Part E, does the solution curve have an inflection point? Yes, it does. The inflection point is where your second derivative changes sign. And our second derivative changes sign right here at 9,000. Okay, so that is also your justification. We have a point of inflection at p equals 9,000 because the second derivative changes from positive to negative. And then part F, use the information you found to sketch the graph of P of t. All right, so putting some points in here, you're going to have an initial value of 4,000, carrying capacity of 18,000. You have a point of inflection here where your concavity changes. That was at 9,000, and that's just a rough sketch. We did not actually calculate when that point of inflection occurs, but we could do that just as well. So the last problem here says, suppose a rumor is spreading through a dance at a rate modeled by the logistic differential equation right here. What is the limit as t approaches infinity of p of t? So once again, what we want to think about when we see logistic problems, anytime they're asking for the limit as t approaches infinity, you got to think, well, what happens as your graph goes to infinity is your graph approaches this y value, which is your carrying capacity. And that carrying capacity, which is the letter m that we have used in our formula, that's what we want to find. That's what our limit is going to be. And so on this particular problem, remember that the generic formula is dp dt equals kp times 1 minus p over m. So if we can get this value right here to be 1, we have a p to the first power out here, we have p to the first power here, the number in your denominator, that is going to be your carrying capacity. So on this particular problem, we need a 1 right here, so that means we need to factor out the 3, which will give us dp dt is equal to 3p, which changes the 3 here to a 1, minus p over 6,000, because 3 times 1 over 6,000 would reduce to 2,000 for your denominator. And what that means is that this 6,000 is your carrying capacity, which is what your limit is going to approach. in the context of this problem, that 6,000 represents the total number of people at this dance. All right, so then the next problem here, suppose a population of wolves grows according to the logistic differential equation given here, where P is the number of wolves at time T in years. Which of the following statements are true? All right, so once again, we see this notation. The limit as T approaches infinity of P of T is equal to 300. They're saying that 300 is our carrying capacity. All right, so what we need to do is take a look at our problem here. dP dt equals 3p minus, I'm going to change 0.01 to be 1 over 100 times p squared would give us p squared over 100. So I'm going to factor 3p out of this problem, leaves you with 1 minus p over 300, and therefore, yes, because this number is 300 right here, that is our carrying capacity, so that is true. Part 2 says the growth rate is greatest when p is 150. If you remember from earlier in your notes, the growth rate is always going to be greatest when you have reached half of your carrying capacity. 150 is half of our carrying capacity, so yes, this is true. The growth rate is greatest at p equals 150. And part 3 says if p is greater than 300, the population of wolves is increasing. Well, if your carrying capacity is 300, that means that's the total number of wolves that your region can handle. So if you have a population of wolves, somebody puts 500 wolves into a region, but that region can only sustain 300 wolves, then that means your population would not increase, it would actually decrease due to lack of enough food or resources for the wolves. So it would not be increasing, it would be actually decreasing if the population was greater than 300. So 1 and 2 would be your only true statements out of this.